Oops. And let's do one more. Yeah, let's do that one. Let's see here. What do we have? Okay. Okay, so we had 2 questions only. One of which was a yes or no question, and the other was for something that we haven't seen in a long time, and for something that you will not see until your final exam. But I guess it's never too early to review, I guess. So Crystal wanted to do an empirical formula problem. Again, this is not something you're going to see to the final exam, but why not? We can practice. So, though I am curious as to what the inspiration was for doing one of these, I'm happy to do it. So with this, when we're given percentages, remember that the first thing we want to do is put them into a unit we can actually work with. So that would be something like grams, right? So we can replace all of these with grams. All right, and so remember we want to question 6 on the homework. Okay, there shouldn't be any empirical formula type things. I mean, I just wrote that homework the other day. Let's see. What chapter is this? Well, we can go ahead and do this anyway, but I don't think any of your homework would have anything like this. I'm downloading it right now since I'm on a different computer, but remember what we want to do is convert all these guys to moles, right? And if we want to do that, so that's not an empirical formula problem, Lamanda. Number 6 is a partial pressure problem. It'll be like the last one, Sherry. Let's see, carbon was at 12.01. And yeah. I mean, that's a good call, and that is a mistake some students make is they see percents and they just assume we're doing empirical formula. So here's your hint. We're not doing this until the final exam, so don't worry about this one. Okay, so, but if you wanted to do the empirical formula for something, and maybe Crystal is just preparing for the final like 2 months ahead of time, that is just fine. So we would want to convert all these guys to moles. Oops, I've put them all upside down as well. Oh, shame on me. Oopsies. Since we're converted to moles, moles needs to go on top, right? 1 mole over 1.008 grams. Okay, 41.05 divided by 32.07 is gonna be 1.28 for 20.48 divided by 16. That's 1.28. 30.74 divided by 12.01 is 2.54. And the last one, 7.74 divided by 1.008 is going to be 7.68. Okay, so now that we've converted all to moles, we want to divide by the smallest number of moles, right? And that'll give us the ratios. If you do all this fun stuff, you get 1126. And so you would, I guess if you were putting it in the order of stuff that I've given you, you would write it like this, and poof, we're done. So that is going to be 678 in the online textbook. If you're using Tro, it's going to be 11, 12, 13. Or is 10 one of those? I can never remember with Tro. I think it's 11, 12, 13 for Tro. The one on intermolecular forces and liquids and solids, gases, and then solutions. So those are usually right next to each other. So they'll be somewhere in that. So I will put this out here. Don't do this until the final exam. You're not going to get any empirical formula questions. So, okay, let me just check Discord. Maybe we have more questions. Oh, sure. Okay, we have a molality question. Oh, yes, we can happily do one like that. Oh, no. Okay, well, that's good to know that you have learned from something. Okay. The molality question. Yeah. Okay, how about... Let's go and figure out what's the concentration of salt in the ocean. Okay, it looks like there are 35 grams of NaCl in 1 kilogram of water. For water, Kf is equal to negative 1.86 degrees Celsius per squiggly m. Is this all the information we'll need? Yeah, I think so. So let me just look up sodium chloride's molar mass so we don't have to add two numbers together. 58.44. Okay. Alrighty, so with this, remember for molality we want to do moles per kilogram. Alrighty, so that's going to be, we're going to have to take our 35 grams, convert that to moles. (35 divided by 58.44 is 0.5989. We already have 1 kilogram of water, so this is actually the same as our molality. So change in temperature is going to be our constant here. Oh, we didn't calculate I yet. What's I going to be for sodium chloride? Yeah, it's 2. Right? 1 sodium, 1 chloride, that's 2 things. And what's the last part, the molality? We have 0.5989 mole. And so, let's do the math. 1.86 times 2 times 0.5989 equals 2.22. Looks like we have 2 sig figs on that, so we would round this to negative 2.2 degrees Celsius. And remember, since this is water, technically we're subtracting this number by 0 to find the final temperature. I'll just do that. Why not? So there we go. We have our final thing. In case we're not sure, this was of course delta T, and this was T T initial. Okay. Let's go ahead. Maybe let's look at, where is your solutions homework hiding? Oh, did I not put it on this part? Let's take a look at the solutions bit while we're here, if nobody has more questions. Let me pop this window open. Is that the window I want? Nope. Is that the window I want? Nope. Okay, let's see. Let me make a new window then. That's the one. So for our solutions homework, we're essentially just playing with stuff and looking at how things work. So, you know, we're looking at how easy it is, for example, go away, how easy it is to pull stuff apart. Oh, we have to press play, by the way. Oh my god, this thing's getting so mad at me. There we go. So we're going to see how easy or how hard it is to pull stuff apart. And how things are going to kind of interact with each other. So when you're doing this kind of thing, make sure you press the little play button at the bottom. Otherwise, it's not going to do anything. So as we go through this, like, you'll be able to just kind of feel with like your mouse kind of how these things are working, so you can see how polar molecules are interacting, how non-polar ones are interacting, and that sort of fun stuff. If we look at another one, maybe the one with molecule sorting or whatever, go away. We can go ahead and put all these, I'm going to just click a whole bunch of molecules in here. And so we're trying to figure out, you know, which one's is going to be non-polar, which one is going to be polar, you know, just kind of how things are working in solution. So if we have two kind of phases like this, do we think this purple one is going to be like more polar or more non-polar, do we think? Just basically base it on like kind of where it's hanging out. So we're able to kind of see on a molecular level how this sort of solution stuff is working as all the particles are moving around each other. So yeah, that's basically your homework. You're doing, this sort of thing, and you're recording your observations. So I mean, you'd probably say the purple one is non-polar because it's hanging out in the oil. The orange thing is probably polar, and this gray thing, who the hell knows? It's kind of just in the middle the whole time. And so all you're doing is, you're kind of just, indicating your observations, and that's it. So this one should not take too long when we do it. So, yeah. Why do I look so red today? Is it this? No. Yes. What was last week's homework? Was that intermolecular forces? Yes, that one will be on the exam as well. Sherry, that's the solutions homework. I put it up like yesterday evening. It's short though, so I wouldn't worry about that too much. Here, let me show it for you. I just had that window. Which one was it? No. Okay, well, it's on Canvas. If you just go to assignments, you'll see it there. It should also be on the homepage. But don't worry, it's pretty short. And then there's just a couple of... Yeah. So the solutions one is the one that I just kind of showed where you're clicking buttons and recording your observations. That one is pretty quick. It should be like half an hour or less. And then the molarity one, I'm only asking you to do 4 of the problems. So on that molarity one, you're just doing the first 4 problems on the first page. That's it. And that's just some, just because the other homework, or the solutions homework, doesn't really cover concentration too much. So I wanted to give you some more practice with concentration stuff. And so you can just turn those in together. So you could put in the solutions one as well as the 4 molarity questions. In the description, it says do exercises 1 through 4 for the molarity. So don't do others. You're going to get confused because those are things we're not covering till the 2 chapters from now. So just do those first ones and that's it. So this will not take as long as the gas homework. And everything is due Sunday. It looks like that was the kind of consensus in your polls. Yeah, by far, Sunday was the winner. So that's it. Okay, is there anything else you'd like to go over? Maybe if you want, take a minute to take a look at the solutions homework, see if there's anything that like jumps out at you as like, what the heck, how are we going to answer this? We could maybe do one of those or something. Yeah, we have a pet picture. Sure. Okay. So I have made up a problem with fun random numbers. We're asked here, what is the final temperature of a substance? We're giving it some heat, and we're going to basically see its temperature change. We're trying to see what the new temperature is going to be. So we're given a specific heat capacity. Oh, I guess we should also we'll need a mass, huh? Of a 46.2 gram substance. Blah, blah, blah. Okay, we're given a specific heat capacity and an initial temperature. So, who was it who likes to to apply the letters? Which letter is this one gonna be for our happy formula? Which letter does this one respond or correspond with? Mm-hmm. That's M. What's this one? Not quite. What units does temperature have? Yeah, that one's going to be Q, right? Temperature would have units of Kelvin or degrees Celsius. So joules would be one that is Q. So remember, Q is heat, which of course makes no sense because there's no Q in heat, but it's the way it is. Okay. What about the next number? What letter does this one correspond with? What letter is that one gonna be? Yeah, that one's C, right? That's our heat capacity. And then we have one more number here. What's this number? Yeah, that is going to be one of the... Oh. Yeah. So I have the gain on pretty high right now, but I can maybe move it a little bit closer to myself. And I can possibly adjust it here. Let's find out what I can do with this. Okay, I don't know how to adjust that. I guess I could just talk louder. That's okay. Well, if this is any better, let me know. Otherwise, like if your volume is all the way up, another thing you can try is if you're on Twitch or whatever, there is a volume for Twitch too. Like, so maybe your volume button is pretty low on that. That could be one thing as well. But if not, yeah, I'm sorry, I don't know what else we can do with that. Specifically, Amanda, this is TI over here. And so that's our initial temperature, right? So we're being asked in this question, what's the final temperature? And so that, of course, would be our final temperature here, TF. So now we can either solve our equation first and plug the numbers in, or we can plug the numbers in and then solve for our TF. We could do it whichever way. What was the mass? 46.2. C was 0.383. Grams degrees Celsius. Okay, so plugging in all that stuff, we're now just left with doing the algebra. So just to make sure that we're all on the same page with the algebra, what we should get is this. Oops. So 4286 divided by 46.2 divided by 0.383, and then we add 22.8. And we're going to get 265 degrees Celsius. And that would be our final answer. And how about we do, let's see. Okay, vaporization, that's the one I'm looking for. Okay. All right, was that one what you were looking for, something like that? Awesome. Okay, let's do another one. How much heat in kilojoules is required to boil 75 grams of acetone. And here are some numbers related to acetone. Okay, so cool. So this question is asking us, how much heat are we going to need to boil a certain mass of acetone? Acetone is, I mean, we don't even need the boiling point or anything, but that's an organic solvent. You might use it as like nail polish remover or something. It is a pretty common substance. So I've given you two delta H's here, but we're only going to use one of them. I want you to be able to choose which one. Which one of these delta H's is going to correspond with the process of boiling? Yeah, exactly. Right? Vaporization is boiling, so that's the one we're going to use. So this is telling us that we're going to get 31.3 kilojoules for every mole of acetone. I didn't give you a molar mass, and you guys have no idea what acetone is. My bad. Let me look up the molar mass for you. Okay, molar mass is 58.08. Acetone, just so you know, OC3H60. There we go. It's technically this. So that's where the molar mass is. Okay, cool. Alrighty. So let's plan this out. We are going here from grams to moles and from moles to kilojoules, right? Remembering grams to moles is always our molar mass. And from moles to kilojoules, that's our delta H vaporization, since we're talking about boiling. All right. We would, of course, want to put our grams on the bottom because we want moles. And then we would put in our delta H. And we would go ahead and solve it. 58.08 times 31.3. Okay, and that answer apparently is 40.4 kilojoules. So that is the amount of heat required to boil 75 grams of acetone. So yeah, these are always kind of, at the boiling point. So what I like to do is remember on your homework you had that big old chart with all those things? I like you guys to calculate the whole thing, but with the multiple choice exam, I can't really do that. That would take half the exam time just to do one question. So you're lucky. You only get one little step at a time here. So lucky you. Alrighty, let's see. Do we have any more in Discord? Nope. Maybe it's because I'm wearing blue. Maybe that's why I'm red. One more with kilojoules. Like, okay, do you want one more like this second one or like this first one? Because technically either one could be kilojoules. I'm assuming you probably want one more like this. The first one. Oh, okay. Sure. Okay. Just making up numbers. Let's hope this is like reasonable. At least I'm just making up numbers. Okay. Alright, so let's go ahead and look through this again and let's see what all the numbers mean. So 321 grams. So again, we're noticing we have a specific heat capacities written in the problem. So that tells us we're definitely using this sort of thing. So let's see if we can figure out what all the letters are going to be. So what's the first number is 321. What number or what letter does this one represent? Yeah, that's mass. Oops. How about this one? You know, I should adjust this. Just so we have our units there. What is the second number going to be? Which letter is heat? Yeah, exactly. That's Q. And then we have the temperature changes, right? So that's T initial and T final. Alrighty. So one thing to note that I've given you, I want our units in joules per gram degrees Celsius. So it looks like on all of these numbers, we have grams, we have degrees Celsius. However, we have kilojoules that are given. So just to make things easy on ourselves, we should probably make that kilojoules into regular joules so that we'll get the units that we want at the end. Does that make sense why we would want to do that? We could find our specific heat capacity in kilojoules per gram degrees Celsius and then adjust. Doesn't matter. I would rather just do it at the front. That's preference on my end, but does not matter. Cool. So this one should just be multiplied by 1,000 if we want to get regular joules out of it. So remember, kilo is times 1,000. Okay, so Q, here it is, 48620J equals M321 times C, which we don't have, and then we have 108 minus negative 4.2. Doing this, that is 112.2 degrees Celsius. Alrighty, so let's have a look here. Let's do our math. So C is going to be equal to that many joules over that many grams, and our degrees Celsius. 48620 divided by 321 divided by 112.2. Hey, this is actually a reasonable number. That's great. And so that one we get 1.3499 whatever 5 joules per gram degrees Celsius. Looks like we need 3 sig figs, so that would be rounded to 3 sig figs. Yes, Kelvin is used with gas laws. You could use Kelvin here, no problem. But that would be a kind of a waste of time, but you could. Remember for a change in temperature, oh no worries, for a change in temperature, Kelvin and degrees Celsius are identical to each other. So this change of 112.2 degrees Celsius is the same as a change of 112.2 Kelvin. You could use either one for delta T specifically. So you can use whichever temperature unit you want. Typically, it doesn't matter for this, yeah. Yeah, that's okay. It's pretty interesting what images I get when, so I use Google as my calculator, so I just type the numbers into the search bar, and sometimes I'll get the most random things that pop up as well. So this one is a bunch of pictures of random I don't even know what these are, door brackets or something. It's pretty interesting. Keeps it amusing for me, I guess. How is the volume, by the way? Is this better? Or did you end up getting headphones and has that worked? Or what's going on there? Okay, cool. Okay, let's see. Is there anything else we'd like to go over? Yep. Freezing and same formula as, do you mean the delta H thing? Or the KF thing? Yeah, you would use the same formula except you use delta H fusion instead. That's it. That's the only difference. Yeah, so if you wanted to instead melt that acetone, you would just use the other delta H, and that's it. So instead of 31.3, you would use 5.7, and poof, there's your answer. So that one, technically there is a formula, but I think it's easier to just use it as a conversion factor. But technically your formula is, what, it's Q something like this, m times delta H, as long as your m is in the right units. I mean, it's just a, yeah, I don't like it. So I pretend it doesn't exist. Okay, cool. Let's have a look here. So, well, the benefit is most of these are seniors, so they are... Oh my god, that's so cute. Okay, hold on. We have to see this. Let's see there. Where are we hiding? There's two of them in there, all squished up together. Yeah, we can do a combined gas law one. Can you see both of them in there? Can't believe they squished into one, but that's Gumbo and Oz in that one. That's the father and son. So they're all squashed together. Okay. Man, this webcam is awful. Okay. Good enough. Okay. Combined gas law equation. Sure. Though I guess I should also... Yeah, I saw that. You'll also notice a lot of mine, or Creature especially, will decide to go on his, Borking crusades randomly, and we have to stop him. But most of the time they're pretty quiet. If the temperature of a gas is quadrupled, and the Yep, cool. Okay, so I'm going to tackle two birds here. So this is a combined gas law problem, but it is also one that you are not given explicit numbers with. So my advice to you is use fake numbers. So we know we have our combined gas law, right? With this, we just need to choose numbers that will fit the question. And then we're going to basically compare V1 and V2 and see by how much it changes. So my favorite thing to do is to use the easiest numbers possible to just make our math super easy. So if I were doing this problem, I would say temperature 1 is 1 Kelvin. And so temperature 2 will be 4 Kelvin. Easy numbers that fit the criteria. It says our temperature has quadrupled, so I am making our second temperature 4 times the first temperature. The pressure of the gas is multiplied by 1/6. So we could say the pressure is going to be multiplied by 1/6. Let's give them atmospheres. Whatever units we want, doesn't matter here. And so we're looking for the volume change. So if we go ahead and plug these numbers in, 6 times V1 over 1 equals 1 times V2 over 4. We can see 24 times V1 equals V2, just cross multiplying there. And so our answer here is the volume will be increased by a factor of 24. This would be, nice if it were a number that we had a word for, like octuple or something, but as far as I know, at least, there is no word for multiply by 24. So I would just put this in a sentence, I guess. So it'll be 24 times as big as it was before. Something like that. So I think a lot of you had asked, how the heck do we do this problem on the homework or whatever? It's similar to this. You would just choose fake numbers that fit the criteria. Again, I like to use the easiest numbers possible. That makes the math easy. But if you want to use your lucky numbers, and your lucky number is 3 pi over 4, you could totally use that and make it work. You'd still get 24 at the end, so long as your thingies fit the criteria. We can do another one. Is this one okay though? Do we see how I made the fake numbers that would fit the problem? Awesome. We're going to do another one. Okay. Alrighty, here we go. Oh, we're doing volume again. Okay. Did not intend to do that, but that's okay. Doesn't really matter. Actually, I guess that's the best one to do for practice. Excuse me. Because volume units are boring. So, remember, combined gas law you use when anything is changed. If you have 2 temperatures or 2 pressures or 2 volumes, use your combined gas law. If you are given one of each, then you use your ideal gas law. But for this, we're going to want combined. Okay, so let's go ahead and label these. It looks like here we have temperatures, and we are given a volume to start. Let's see, can we just plug these in right away? I'm going to just solve for V2. I always like to do that with this equation. But again, you do not have to do that. You could always just plug in your numbers and then solve for V2 at the end. No problem there. Okay, so looking at this, if you were to plug these numbers in right away, it would make me very upset. Why? Why would I be upset? Indeed, that is one thing we're going to need to do. So we have noticed we have different units here. Those are not going to cancel out. So we are going to need to change one of them. We could either change the torr into atmospheres, or we could change the atmospheres into torr. Whichever one you want, it does not matter. We just need them to have the same unit. What else is problematic here? Indeed, we cannot use degrees Celsius. Because if I had made the temperature instead 0 degrees Celsius, we would be dividing by 0. That would not make sense, right? Or if I made it negative 10 degrees Celsius, we would get a negative volume then, which also doesn't make sense. Volume can never be negative. So, yeah, Kelvin is the only way, because Kelvin can never be 0 and it can never be negative. So, cool. All right, so since you were the one to answer, would you like to convert the torr into atmospheres or the atmospheres into torr? I'll do the temperatures. I hope I can do this. Let's see. 285.15. And then the 10 degrees Celsius will turn into 283.15 Kelvin. Atmospheres. Okay, so that's okay. Yeah, whichever one does not matter. So let's go ahead and do this. What's the conversion between torr and atmospheres? Yeah, it's 760, right? So doing this, 2214 divided by 760, looks like that is 2.9 atmospheres. Okay, so now we have all our units. Either they're the same unit or they are in not using Celsius. So now we'll be okay. So V2, I'm going to have to scroll up a bit on this one because I've forgotten all our numbers by now. Okay, pressure first was 2.913 atmospheres. We had 10 liters and 12 Celsius, which was 285.15 K. Our second pressure was 16.8. And our second temperature, 283.15 Kelvin. Okay, looks like after all this crap, we're going to get 3 sig figs anyway, so. Alright, just plug and chug at this point. So that number times 10 times 285.15 divided by 16.8 divided by 283.15. Doing all this fun stuff, I get 1.75 liters. And so just as a checking point, we did say that in the question the gas was compressed. So we are expecting the volume to go down. And lo and behold, indeed it did. We are seeing that our second volume is lower than the first volume. So just to make sure your answer makes sense, if you got 200 liters, that might be problematic. That probably means you did something incorrect there. So, always just, keep in the back of your mind, make sure your answers make some sense as to that. Okay, actually, it looks like we are out of time. So, of course, if questions come up, post them on Discord over the weekend, and I'll try and get to them if I, when I can. So, I'll try and have your homework keys up so they'll show up at Monday at midnight, so you'll be able to see them right after things are due. Okay, let's see, what class are we? This one. Okay. There are your notes. So those are posted. Hooray. Wow, this is creepy. I post them always at 10:03 a.m. That's weird. Oh, there's one at 10:16. Oh, okay, well, fine. It's no longer creepy. Okay, yep. Good luck on your exam. There will, of course, not be any meeting for us on Monday, so I will see you all on Tuesday for chemical reactions. This is where the real fun begins. And again, I will try and have all your stuff graded before the drop date, which is, I think, either Halloween or the day before. It's somewhere at the end of the month, so it's either the 30th or 31st. Double check it if anybody is thinking of dropping, but I'll try and have everything so you'll be able to make the most informed decision possible. Alrighty. I will see you Monday.